Let me introduce you to normal distribution, which is one of the most commonly used distributions in statistical analysis and even in everyday conversations. A large body of academic, scholarly, and professional work rests on the assumption that the underlying data follows a normal distribution. The defining characteristics of normal distribution is this bell-shaped curve, which you're familiar with from your textbooks. Mathematically, normal distribution is presented by this equation. We can say that the normal distribution relies on three inputs, and F stands for functions, a function of x, mu, and sigma. X is your data. X is a random variable, and it can attain any very reasonable value. Mu stands for the mean, and sigma is standard deviation. And the mathematical formulation is right here, which is 1 divided by sigma times, and then the square root of 2 times pi. Pi is the 3.14 or 22 divided by 7. And then you have the exponential here. Do not forget this minus sign. So exponential of this entity, which is minus, and in the numerator, x minus mean, or x minus mu whole square, divided by 2 times sigma square. So let me explain. 1 divided by the standard deviation, and then the square root of 2 times pi. 2 is known and pi is known. So is the value for exponential. And what is not known is the sigma, which you obtain from the data, that is standard deviation, and the mean, which is also coming from data. So you have the mean and the standard deviation, and x is the random variable whose mean and standard deviation you're using. You put this all together, and then you get the normal distribution, the bell-shaped curve that you saw earlier. I also introduce you to the standard normal. A standard normal is when we say that x is a variable that has a mean 0 and standard deviation of 1. So what's mean 0 and standard deviation 1 look like? If you replace mu with 0 and standard deviation or sigma with 1, the equation is reduced to this entity, which is 1 divided by 2 times pi. Notice the sigma here, which I've grayed out a bit so that it doesn't interfere. Sigma is 1, so 1 times anything would be the same, so I've removed this. And then e to the power minus x minus mu, but because mu is 0, so x minus 0 is x, so x squared divided by 2 times sigma square. Sigma, remember, is 1. The square of 1 is 1, so 2 times 1. So removing sigma, because it's 1, and anything multiplied with 1 is the same entity. So how do I generate this normal density or a bell curve? Let's assume that the underlying variable has a mean 0 and the standard deviation of 1, and x varies between minus 4 and 4. So the mean is 0, and the minimum value is minus 4, the maximum value is 4, and I would substitute these minus 4 to 4 values in this equation. This is the only thing that's changing. The x here is the only entity that is changing. And let's see if this could generate the standard normal curve.
Let us do this in Python. We'll use the matplotlib function, which you are already familiar with for the graphics, NumPy library, as well as the norm.pdf function in the SciPy stats library. In this example, I have used increments of 0.1. This will generate the standard normal curve that you hear about in statistics.